Welcome. In this video, we are going to solve some networks of dry gas wells, gathering networks. And we are going to do one first example graphically, and then we're going to solve an exercise in Excel. So consider this is using data from problem 4 from exam in 2017. And it's we have addressed this problem earlier. That is that we were solving the open choke case, but now we're going to solve it's assuming that it's choked. Okay, so we have these two wells that are producing to a common pipeline, and they have chokes. And we assume also that the downstream of the choke, they are very close to each other. They are very close to the junction. So actually, we don't have to solve this little flow line, but actually we can say that the downstream pressure of the choke for both wells is the same and is equal to the junction pressure. So now the question comes, is it possible, we get a question that is it possible to produce 500,000 from each well in this configuration? If it's possible, what is the choke delta P required in each well? We saw before that the equilibrium rate when these chokes are fully open, it's actually much more than 500,000. So we know that, or we have the intuition that if we want to have a rate lower than that, we should be able to achieve it by choking, by breaching the pressure drop. So our strategy is going to be, as is shown here, we have a, we are going to go first from reservoir, bottom hole, all the way to the wellhead, okay, just before the choke. And we're going to calculate the available pressure there. And we're going to do that by fixing this 500,000 rate for each well. Okay. And then we are going to, from the separator and having this 1 million, now it's going to be the sum of the rate of each well. Okay, now we're going to calculate with the flow line equation, what is the pressure here at the junction. And then we're going to compute wellhead pressure 1 minus P junction and wellhead pressure 2 minus P junction. And we're going to verify if it's positive. If it's positive, that means that the rates, I'm able to produce them and it's fine. But if it's negative, that means that is not feasible, the rate. So we've got these curves. Let's me. This is for well 1. Okay, this represents the curve of IPR plus TPR. I'm going to open PowerPoint to make it simpler to get the points. Okay, so we said first in well 1, we want to produce 500,000, okay, which is going to be here. So let's take a line. And then we go here. Let me just change the color. Then we put another line just to read how much. You can also use a web plot digitizer for this if you want. Okay, so that's approximately unitarian steps of this will be 104, 108, 112, 116, 120. So this is 116. So half is 118. So this will be maybe 119. Okay, so we obtained from here approximately 119 bar. Okay, approximately. P, this is the pressure that is available at the wellhead when I'm producing 500,000. Okay, so let's create one more slide to calculate the one for well 2. which is this chart. Remember, this chart is including IPR and TPR. Okay, and again, the same thing. I come with, let me just copy. So I'm going to use all of these again. And 500,000 in this case is here. Which is also about, let's see if we are making things. Okay, so this is about a bit less than 100 and maybe 104, 108, 112, 114, 113 bar. So the wellhead pressure are very close, both 113, 119 bar. And then let's repeat the same for the flow line. But in this case, be careful, because here I'm not producing any more 500,000, but now the pipeline is carrying actually the rate of both wells, which is 1 million. Okay, and this is here. So we have 30, 32, 34, 36, 38, and 40. So we have 36, then 37. So this will be maybe 37.5. So the answer here is very clear that we have more energy. Okay, so we have, if we want to produce a rate of 500,000, okay, standard cubic meter per day from that well, I need to have a wellhead pressure of 119 bar, okay, roughly. And also here for well 2, if I want to produce 500,000, I have to have roughly a pressure of 113 bar. Okay, but if I want to produce a rate of 1 million, 1.5 plus 0.5, then that means that I need to have a required pressure at the inlet of the flow line on 37.5. Okay, so that means that the delta P, I have to choke both wells, okay, and I can calculate how much that will be. So let me just copy this to the journal. This is for well 1. For well 2. And the pipeline. Okay, so then I can just calculate and say that the P choke 1 will be 119 minus 37.5. And the delta P of choke 2, it will be 113 minus 37.5. 91.5 for the first well, and for the second well, 75. There's something wrong here. There is an error with the other one. 81.5. Okay, and that's it. So we have solved the problem, and we found that yes, it is possible to produce 500,000, and this is the delta P of the choke. Okay. And we found the delta P of the chokes. You might find also some case in between that you either both. So it could happen that this pressure actually gives you, let's say, something below this pressure. Okay, let's say both give you, I don't know, for this rate, they give you less than that, 30, 36. Okay, and that means that you have to, in that case, you have to adjust these rates until I get that the delta P is equal to 0. Okay, natural flow. But it could also happen that actually I found that one of them, the choke is positive, and for the other one, the choke becomes negative. So in that case, I might have to adjust just one of the rates and not both of them. Okay, but this example, graphical example, is just to give you a feeling how do you solve the network. Okay, and it's very different if you want to solve it if it's open choke, where I have no control of the rates. I put this system together and then it produces something that I want to calculate. And there is also one in which I want to produce some rate, and it turns out that the system is choked. You see, in this case, it was very simple. I didn't have to do any iteration. I just simply imposed the rate on each well. Okay, and then I calculate the pressure and then simply verify that the delta P is positive. Okay, so it's very simple, it's very straightforward. While if I have to do solving, then it becomes a bit more cumbersome. So now that the other examples I'm going to make, it will be 4 examples, and it will be solving a similar network, but in this case, we are going to have, so there are again 2 wells with different properties, but now I have a flow line downstream the choke that I reach a junction, but essentially the rest is the same. Okay, I'm going to put a link someplace here, but so you get access to the Excel file. I'm going to open it here on my computer. And we're going to look at different cases of this network. Okay, so first we have the case has a graphical solution we did earlier that we just want to find no choke, open choke rate. Okay, so here you have the properties, the reservoir pressure, the C and the N, that's for the IPR, the S and the CT, that's for the tubing, the flow line, that you have one, which is the main pipeline, and separator pressure. So let's start. I suggest that we have a very interesting point here in this, which is the junction. Okay, we know that the pressure seen from this side, the pressure seen from this side, and the pressure seen from this side, it means that all of them should be the same. Okay, and that's what we are going to try to use with the solver of Excel. We're going to say, well, change this rate, okay, until that pressure becomes the same seen from here, and seen from here. When it's seen from here, is the available pressure at, remember the choke is open, so it will be at the end of the flow line for well 2. This is the available pressure at the end of the flow line for well 1, calculated considering IPR, TPR, and the flow line equation. And then this one is the required pressure required at the inlet of the flow line, okay, seen from separator. So we can have, so to start getting, so I suggest here we start at least with the wells, okay? We start with the reservoir and then we move forward. So the first equation you find there is the IPR, which is this back pressure equation. So in this equation, I can go two ways, okay? I can assume the rate and then calculate the pressure, or I can assume the bottom hole pressure and then I can calculate the rate. What I suggest is that at the rate usually we don't have, if we are new to a system, we're not acquainted with the rates or how it produces, it might be a bit difficult to find a good range for this Q. Okay, is it 500,000? Is it 100,000? Is it a million? Is it 3 million? Okay. So what could happen if you use this approach? You see here we are clearing out the flowing bottom hole pressure. Okay, you see that if we guess a too high number, that this means that this value under the square root is going to be negative. Okay, so that means that this I'm going to have some issues with this in the value, especially in the solving process. When I'm solving that, it might happen that the value of Q I guess is actually too high. Then this becomes negative. Then this has an value error. Yeah. So what I suggest is that we, instead of guessing Q, we start guessing PWF. PWF, we know where it is. We know that it's usually should be between atmospheric, right? And it should be below reservoir pressure. Okay, so I wrote it here. We prefer to assume PWF because I know the upper bound. So let's do that. Let's say we're guessing this pressure. And let's start maybe with we can say 60 bar, okay, for both. Then we use the IPR equation with giving me, in this case, rate. And this equation is using back pressure coefficient, Dn, reservoir pressure, and here is the pressure. And see, I don't block any of these because when I want to drag this cell down, I want also to be dragged and apply for all of these properties for well 2. So I gave 87 and 4 half. So even though they have the same pressure and they have the same reservoir pressure, their deliverability is almost half. So this means this one is, you see here that the C is actually higher than DC. Okay, so that might be the reason. Then I move from bottom hole to wellhead. For that I use the TPR equation, tubing, and what I need is I'm moving concurrent, so I should move, I need the TP2, okay, pressure at the discharge of the tubing, okay, which is essentially the wellhead pressure. And this requires the CT, again, I'm not going to freeze it, P1, which is the bottom hole pressure, and the Q, which is here. And you see I end up with 55. There is much here, 3 bar, so it's a very big tubing apparently. I have almost no pressure loss at the tubing. In the tubing, make sure things make sense. Okay. And then we calculate the pressure at the junction. That means I'm moving now from here, I'm going to say fully open choke, and then I'm moving and calculate the pressure here. Okay, so that means wellhead pressure plus this flow line. And this flow line we're going to assume is horizontal, and we can use our flow line equation. I think we call it line, okay, P2. Again, I'm moving from the wellhead to the junction, and there I have, I'm moving with the stream, okay, with the flow. So C, then P1 is this one, then Q is this one. Okay, and there is almost no loss there also. 50 is close to 1 bar. Okay, and now I have to go the opposite way. I have to move from here to here, okay, to find out what pressure do I have in that junction. So first I calculate the rate, which will be the sum of these two. Then I calculate the P junction, which will be line, but in this case, be careful, is P1 because I'm moving from here to here. So I'm going counter current. I'm going against the current. So this is P1 as defined by this direction, and this is P2. Okay, so I have P2 and I want to find out P1. Line P1, and this is using DC, and the pressure that it has is the separator pressure, and the rate is the sum of both rates. Can you see again? Very little. So now the main task is I want to make all of these the same. Okay, you see these are the same, but they are not the same with this one. So I could do and try to increase a bit the rate. Okay, to increase the rate, I might have to lower this one. Okay, you see now it goes to 50. 50, they get a bit closer, so I get 45. 45. Okay, they get also a bit closer, maybe even 40. Okay, now they're getting very, very close. Okay, but instead of doing that manually, I want to do that with the help of the computer. Okay, so one technique is to try to compound all of that, all of those differences in one error, okay, that I'm going to have here. One way to do that is first to calculate the average of all of these. The average. Okay, and then I want to say the difference between each one of them minus the average. And I'm going to square that difference because I want to sum all of these differences, so I don't want them to cancel with each other. If one difference is positive and one difference is negative, I have to block this cell. Okay, so you see is, first I calculate the average of the three, and then I say the difference between each value and the average. Okay, and then to calculate the total error, I say is the sum of these. So if we go back here to our journal, okay, this is the objective variable is the average minus J1. Well, it should be the opposite, right? We were doing the PJ1 minus PJ average. And that's what I'm going to minimize. Okay, if I manage to minimize all of these, that means that all of them are the same. So I use the solver. And the solver, I want to drive this cell to a value, in this case can be minimum, right? Because it's you cannot be negative. It's a squared quantity, so it cannot be negative. And I want to change these two. And if I want to help a bit the solver, I could say also that these two parameters have to be less or equal than reservoir pressure. Okay, and it found a solution. So essentially very similar, 38 and 34 flowing bottom hole pressure, and the P at the junction is 31. You see the same for all of them. Well 1 produces 100,000 and well 2 produces 49,000. Okay, for a total of 150,000. This is a small network, so this could be an onshore, small onshore network, but it not offshore. The rates are a bit too small to be offshore. Okay, so this method to create this error function, to minimize that error function, you can have also different ways that you can solve this network. Okay, this is just one approach, trying to condense all of these differences in one equation. Okay, but you can also use different approaches. Okay, so I'm going to let me see if it was already copied. Not sure. Okay, this is I did it previously, so you see the numbers are Makes sense. I don't know why I had this big space here. Okay, but these are the numbers, and this is just a screenshot of how the solver is set up. If solver for any reason in your computer, remember if this is not available, you can go to File, Options, and then Add-ins, and then click here on Go, and you can select here the solver add-in. So that means that it's now going to be shown here at the top. Okay, so that's so that was the first case in which we are running an open choke. And if you can visualize, let's start to think a bit of network the way we do it in a commercial software. That is, you have some input which might change. Okay, in this case, what you might think it might change, you don't change these properties usually unless you recomplete, you do a stimulation, for example, you change the tubing size, but this usually is constant and is what we call the system parameters. Okay, then we have something that does change, which is the reservoir pressure. That's usually changing with time. And if we have nothing else to modify, that means we don't, it's an open choke, we don't have compressors, we don't have pumps, etc. Simply we have a model, we have a function that when we run it, that's going to give me the equilibrium conditions. That means the bottom hole pressure on each well, wellhead pressure of each well, the junction pressure, and the well rates. Okay, and if I have, you think of a on a software, for example, I'm going to have also the pressure along these elements. Okay, I'm going to have the pressure and temperature along the tubing, along the flow lines. Okay, now let's go to the other case in which we have a choke. Okay, and that's the second tab here. Okay, we have a choke and we know that we want to produce 8,000 and 4,000 from each well. Okay, and the strategy is very simple. Is just like we did before. And I say this is like the simple option, and this typically is not available in commercial software, and we're going to see later how it is done. But essentially, I fix the rate, and then I go to the point of the control element, okay, in the choke, is where I have a pressure discontinuity. Okay, so I go with the rate, go IPR and TPR, and calculate wellhead pressure. I stop there because that's where I have my control element. And then I go from the separator with the rate of the two wells to the junction. I calculate the pressure at the junction. And then from the junction, I go to each well, to the downstream of the choke of each well with the rate of each well. And then I verify that this difference is actually positive. So let's do that. Let's close this one. We don't need it anymore. Okay, so this is the Q of the well. I'm moving now from reservoir to flowing bottom hole. Okay, so this will be IPR, PWF, and the C, the N, reservoir pressure, and the rate that I want to produce. And that tells me if I want to produce that rate, actually I need 69. Okay, because, and it makes sense because the rate where it had no limitations, where it had no choke, actually was 100,000. Okay, so that means that as I'm choking, and actually I'm getting a rate 80,000 lower than that. And the same should be here. If I leave it unchoked, it should be 49,000, and here I'm producing 40,000. Okay, so let me just drag it down. 66 and 69. Now let's move to the wellhead. So for that, I'm going to use tubing P2. Okay, I want the, and this is the tubing coefficient, the S. P1 is the flowing bottom hole pressure, and the Q is here. You see I have like a 5 bar, and here is like a 3 bar pressure drop in the tubing. And now I stop there because that's where I have my control element. Okay, I stop exactly there. And now I have to go from the other point, the other boundary where I have my pressure is known. I have to go back uh, to the choke. So for that, I'm going to sum and to find out what is the rate going through the flow line. And then I'm going to use line P1 in this case. I want to know the inlet pressure to the line, and the C of the flow line, the P at the end of the flow line, and the Q. Okay, very little. So now I make this equal because both wells, they will have the same pressure. Okay, and now when I have that, now I move from from the junction to each well. Okay, so if maybe we use this drawing, which was a bit better, we're moving from here to here with the rate, and from here to here with the rate. Okay, to calculate the pressure DC stands for downstream the choke. Okay, so I say this will be line P1 again. I have the pressure at the discharge and I want the pressure at the inlet. And then the C here I have to be very careful is this C of the flow line, the P2 is this P, and the Q is this Q. Okay, so almost no pressure drop. And then the delta P of the choke will simply be this guy minus this guy. And you see that actually it's positive, so that means that I can produce a rate, and these are the delta P required. So let's see, I think that I got the same numbers. Okay, 33 and 32, similar, and 69, 66. Okay. So if you see so far, what have we done? So we have decided not to model the choke explicitly. Okay, we have just said there is a choke here, there is a component, and we are not interested how it works. We are not interested to see how it is modeled. And although in previous lectures we have seen how the equation looks like, but actually we are not modeling it explicitly. Okay, we are just calculating the delta P and making sure that this is positive. If it's negative, that means that the choke should be fully open and actually I don't need to model it also. Okay, but commercial software doesn't work in this way. Unfortunately, we didn't have this semester the chance to work with GAP or with Prosper. This is commercial software that I can use to do these computations, but it doesn't work like usually this option is not available, simply to impose the rates and verify the delta P. Okay, so option 2 that I have, and this is what the commercial software is using, I have two choices. Okay, one is, and that's what they prefer usually, is that I provide a delta P of the choke. I don't introduce the model of the choke explicit, okay, but I simply say the choke has some delta P. And then when the rate that is given, this 80,000, I try to adjust this delta P choke until I get the rate given. Okay? The other option is to include a choke equation that is a function of rates, pressure, and the opening. And then I'm changing the opening until I get these rates. I know it might seem a bit confusing, but just bear with me and we're going to do an example how it is done. So remember the network function we have earlier, okay, in which we give reservoir pressure, we give network model, we have some network parameters, and that gives me the solution, okay? But now this network actually have one more component, which is the delta P of the choke. Okay, so depending how big this delta P will be, okay, I will have different equilibrium conditions. Okay, so if I run it with 0, that will give me the solution of the natural flow. But if I run it with 5R in each choke, then I will get a different solution. Okay, so let's solve that example next, okay, which is now on the third tab here on the sheet. Okay, and in this one, we're going to solve it saying, you see, it's exactly the same sheet as before, okay? But now we have one more column that says delta P of the choke, which is going to be 20 bar. This is an input now. I'm saying I have the same network, but now I apply a delta P of 20 bar, and I want to see how much I produce. Okay, so let's try to solve it, and the strategy is going to be more or less the same. Okay, we go from reservoir to bottom hole, from bottom hole to wellhead. But now we actually are not going to stop there because we already have the delta P, so we can calculate that pressure. Okay, now we are going to move from this pressure to the junction, and we are going to stop there. Okay. And then we move from reservoir to bottom hole wellhead, and with the delta P given of the choke, we calculate the pressure downstream and then pressure at the junction. And then we're going to repeat like our network calculations on this junction, okay, that the pressure seen from this side and from this side and from this side should be the same. Okay, so let's see how that works. We have to assume some number here. Let's say we can assume maybe 50 for both. Okay, then we use again the IPR equation with the rate. Remember, we want to guess on the pressure because we know the upper bound. Okay, but you could also guess on the rate if you want. C and N and PR and PWF. And then wellhead pressure is tubing P2, the discharge. Then this tubing is C, is S, is P1, and the rate. Okay, after we have reached, now we have reached the wellhead for both wells, and now we have, the problem before is that we didn't have this delta P, so we had to go backwards. But now actually we have it, it's a user input. Okay, so now I will say that this D is this number minus this number, 25. And then I can move further to the junction in which is line P2. Okay, because I have the pressure at the downstream of the choke entering this flow line, and I want the pressure at the junction, which is at the outlet of this pipe. So this will be flow line, P1 is this one, and then Q is this one. Okay, it gives me 23, not much, and here it gives 26, 1 bar. Okay, very little pressure drop. And now I stop there because that's as far as I can get. Now I have two. So now I go from the separator counter current to the junction using the flow line equation. So first I have to compute these two. And then I calculate P at the junction, which will be line P1, okay, because I'm moving against the flow. C flow line, P2, and the rate, 30. And then I want to make all of these the same, okay, by changing these two. It's exactly the same case as the natural flow, but now you see that the equilibrium point, the choke is not fully open. The equilibrium point is still at the junction. It's exactly the same as the previous case, but now we simply have this as an input. Okay, so now we don't have a delta P equal to 0, but we have actually a value. Okay, so for doing, we repeat the same. We calculate first the average. And then we calculate an error, which will be, for example, this minus this one. And I remember to block it squared. Okay, remember I square it because This difference can be in some cases positive, can be negative, and I want that when I sum all of them, they don't cancel out. Okay, because it might be that this one has +3, this one has -3, and then it will be, the sum will be 0, but actually it's not guaranteeing that all of them are the same. Okay, now I use the solver and I say, solver again, please send this cell to minimum by changing these two, and I can add some help that I say these two are less than reservoir pressure. Okay, and actually now it found a solution. You see all of the pressures are the same. The delta P choke is 20, 20, and I say, well, I need to have, it's 90,000. Remember the fully open choke was 100,000 and 44,000, while the open choke was 49,000. Okay, if I change these numbers now, I choke a bit more. What will happen is that this rate should be going to 0. Okay, it should be reduced. Okay, now you get 82,000 and you get 40,000. And that's the way commercial software works, okay, that you give this delta P and then you calculate the rate. Okay, so let's see, these are the what I did previously, and actually here I put 5 as delta P, so let's check with 5, what do we get? Much lower. Okay, here you see, very important, what we got was error, okay, because these initial seeds probably are very bad. So let's see, let's try with 50 to see if that gave, okay, now that it converged. Okay, it's very sensitive to the initial seed. So we got here 42 and 49, and I think that's what we have in our sheet. Okay, this happens, you see here, it's this solver is based on a gradient-based method to find the root. Okay, so for example, you have here is like a Newton-Raphson. So I have an initial point, I evaluate the derivative, and then I shoot the derivative to make the function equal to 0 to approximate. And then after I have that, I calculate a new derivative and I approximate like that to the 0. But if you see if the initial seed for some reason and the function here is a bit flat on the right side, if it's poor, okay, you see that it's going to shoot and it's going to give you a bad number. So if I try to use this number, for example, a negative pressure, then it's going to fail. Okay, here we have the case of 20. So now the last case I have for you in this video is what happens, how I can use this model to find delta P chokes such that the rates are the same. You remember when we got initially this problem, we simply went, okay, and simply forced the rate, and then it was simply a very simple run, okay, but now we have to use this method, okay, to calculate such that these two rates are 80,000 and 40,000. So think of it is a bit, going back to our network model, is a bit like that. So we now solve all of these, okay, that we have here. We have a model that we have in Excel where we provide reservoir pressure, we have some parameters, and we have the delta P of the choke, and we calculate the equilibrium conditions. That works, okay? But now additionally, actually I'm given a target, okay, these 80,000 and 40,000, and I want to calculate the delta P such that I achieve those targets. Okay, so that is equivalent to have a solver on top of this network model. So I get a target, I read the rates per well, I compare with the target with the well. If they're not the same, then I change the delta P of the choke. But you see, this is a bit cumbersome because this actually has a solver inside. Here I'm solving the system of equations. Okay, so it looks something like that. I have a solver and I have another solver here. So in Excel is not able to do that. Okay, they have it in GAP. They have two levels of solver and they use it like that. But in Excel, I cannot have two nested solvers. Okay, so what I do is I try to merge these two solvers. Okay, and what I do is that I add a so to this problem, I'm going to add a constraint that this one has to be equal to 80,000 and this one has to be equal to 40,000. Okay, so let's do that. So it's Q target. Q target, this will be in these units. Okay, then it was here 80,000 and 40,000. Okay, but now I'm not only changing these two, but I have to change also the delta P of the choke because these are the numbers I have to find. So this one won't be read anymore. It's not user input, but it's going to be solver, okay, modified. So I come here and I modify my solver and I have to say, yes, minimize that error yet, okay, by changing not only these two, but these two. Okay, so these four numbers, okay. And then I want to add the constraint that these two should be positive, greater than 0. And also I want to add the constraint here is where I say that this rate should be equal to this target. And this rate should be equal to this target. Okay, and then I solve and I got an error. So let's see, maybe we can use a better number, delta P choke. I think it will be with, we tried before with 30, I think, right? And 30 was similar. 20. This one, I think, was 60, and this one was also 60. Okay, the initial condition is very, very important. Okay, now it converged, and it told me that actually to get those rates of 80,000 and 40,000, I have to choke with 33 and 32. Okay, which I think is what I have. Okay, here these are the Q targets, and this is 33. Oh, because here is 30,000, so it says with 52. Let's try that case. Okay, 33 and 52. And that's how I managed to put the two solvers together. Okay, I didn't need to have two levels of solver, although in many commercial software I have it like that, but I managed to simply by modifying the solver of the network to have that. Okay, that's all I had for today. Thank you for listening and good luck.